So Drift is an exhibition curated by Sunny Kerr and produced by the Agnes Etherington Art Centre, the Arthur B. MacDonald Canadian Astroparticle Physics Research Institute, and SNOLAB. It began as a residency in 2019 with 4 international and Canadian artists: Joel Toms, who will be speaking today. Hi, Joel. Anne Riley, Josepha Njam, and Nadia Lichtig. So through their residency, they worked with physicists, chemists, and engineers at SNOLAB who are contributing to the search for dark matter. And it is through their transdisciplinary exchanges with scientists that the artists have created artworks, sculpture, installation, textile, and video that emerge as multisensory agents in the search for an experience of dark matter. We would love for you to come and visit the exhibition in person if you feel comfortable. All details for booking a visit are on our website, qag.ca, and I'll put that link in the chat. And we're open Tuesday to Sunday from noon to 5 p.m. The exhibition will be on at the Carleton University Art Gallery until April 3rd. And I really wanted to thank Simon, Gurpreet, and Joel for being part of this conversation, and to Moira and the Faculty of Science for this collaborative event, and to Sunny Kerr, the curator of the exhibition, me and the whole QAG team, Heather Anderson, Sandra Dick, Patrick Lacasse, Victoria McGlinchey, and Danielle Printup are so appreciative of your work and collaboration on bringing this exhibition to Carleton University. So thank you so much. And I'd also just like to thank our funders, Carleton University, Canada Council for the Arts, and the Ontario Arts Council. Okay, so now I'm going to give brief bios for Simon, Joel, and Gurpreet, and I'll put their full bios in the chat. And then I'll hand it over to Gurpreet to start the conversation. Gurpreet Kaur is a PhD candidate in astroparticle physics at Carleton University, working with the Deep 3600 housed in SNOLAB since 2017. Dr. Kaur graduated with a bachelor's degree in science from Punjab University, India in 2014, and received a master's degree in solid state physics from the Punjab Agricultural University in India in 2016. So welcome, thank you, Gurpreet. Joel Toms is a quantum ecologist, an artist oscillating in semblance with contemporary Greenwich Mean Time. He's the founder of the Radioamnion Ocean Sound Art Project, coordinator of a number of eco-futurist art, science collectives, and a lecturer at Goldsmiths University's MA in Art and Ecology in London, England. His work has won awards and is held in collections and is shown internationally. So welcome, Joel. And Dr. Simon Veal is an assistant professor in the Department of Physics at Carleton University within the Arthur B. MacDonald Canadian Astroparticle Physics Research Institute. He received his PhD at UBC and was a Chamberlain Fellow and NSERC PDF Lawrence Berkeley National Laboratory from 2014 to 2017. So thank you so much. Thank you, Simon, for being here. So thank you so much, everyone. And Gurpreet, over to you.
Thank you very much, Fiona. Hi, everyone. And as Fiona already said, I'm a PhD candidate at Carleton University. I'm working with the Deep 3600 project for the search of dark matter. And I'm really very excited to have a chat with Joel and Simon about the dark matter search, and especially how these two different fields work together and how we are looking for dark matter search. So let's have a chat with Simon and Joel. Firstly, I'll start with the dark matter as such. So I have a question for you, Simon. Could you please tell us what dark matter is exactly? What's the importance of dark matter and why we are looking for it? And what are the other fields which are actually connecting to the search of the dark matter with us?
Thank you, Gurpreet, and hi, everyone. Thank you, Maura and Fiona, for organizing this event, and thank you, Joel, for being accepted to participate. So what I'm going to give today is the physicist's perspective on how physicists and artists look for dark matter, and I'm really looking forward to hearing Joel also about the artist perspective. And so the first question that was asked by Gurpreet is, what is dark matter? And so in a few minutes, dark matter historically came from the galactic rotation curve problem. A galaxy viewed from above, a spiral galaxy looks like this with an amateur telescope. And taking a better look with the Hubble Space Telescope, this galaxy, the Whirlpool Galaxy, looks like this. About 100 billion stars rotating around the center of the galaxy that we can see here. What astronomers have observed in measuring the rotation speed of these stars around the core is that there's a mismatch between what we expect from the mass that is visible, the mass that of the stars that we see in the galaxy. That this amount of mass predicts that stars should rotate at a certain speed. And so this graph here is speed as a function of radius from the center of the galaxy. And the dashed line is what is expected. As you can see from the data, the speed at which these stars rotate around the center is much higher. This was first observed by astronomer Vera Rubin in the 1970s. And she's made these observations in multiple spiral galaxies. And this was not understood until later when the dark matter paradigm came about. This is not the only evidence that we have for dark matter. There's also more direct evidence in the form of galaxy clusters. The bullet cluster, pictured here, is a cluster of galaxies. In fact, it can be described as two clusters of galaxies that have collided together. And as they've collided, the gas, the intergalactic gas that you see here, emitting in the X-ray, is shown here in pink, it's highlighted. But there's extra matter that we know is there through an observation technique called gravitational lensing. And this is highlighted here in blue. And this extra matter has passed through the ordinary matter and the extra matter, with the dark matter, to end up on the other side of the collision, while the ordinary matter was slowed down. And so this is another, this matter excess observed is another clear sign of the existence of dark matter. There's also other clues in our theories for the evolution of the universe. This is a time lapse going from left to right, going from the Big Bang to the present day. It's an artist's conception of the evolution of the universe. Dark matter here in the evolution of the universe is acting as a catalyst. It's bringing what used to be a more diffuse concentration of matter together in a quicker way. In other words, dark matter enhances the formation of the galaxies, such that today the galaxies have a structure that would not have been reached after this length of time, the age of the universe, in the present form, without the presence of dark matter. And so, in other words, our models for the evolution of the universe to the present day require a large amount of dark matter to exist. If we go to previous times, and if we look at further and further distances, the light that is coming at us from objects that are very distant has taken sometimes billions of years to get to us. If we look to the edge of the observable universe, we look backward in time, close to the in what's called the afterglow light pattern, or the cosmic microwave background, and we can make a map of this surface of the last scatter of light. This is basically the surface, the time at which the universe went from opaque to transparent. And some of the light that we detect came from that time in the age of the universe. And scientists have made a map of this, of the sky at this distance, at this time in the evolution of the universe. And what can be inferred from the very small temperature differences between some parts of the sky and others, making a fit to the correlation patterns, is that the universe is made of 5% ordinary matter, 27% dark matter, and 68% dark energy. In other words, we get this that's called the cosmic pie chart. And it's a staggering result. It means that all the ordinary matter, what we experience, what we see with our telescopes, is only less than 5% of all the matter in the universe. And so the discussion about dark matter really unites two subfields of physics. Astrophysics gives us very clear evidence that dark matter exists, and they tell us how much dark matter there is. But we don't know what dark matter is. In particular, we don't know the mass of dark matter particles. So it can go any way from ultralight dark matter. This is at the smallest masses that we can ever detect. 1 GeV is about the mass of a hydrogen atom. So you can see this is even much smaller. Hydrogen atom, and then one mass Planck here is about the size, it's about the mass of a grain of sand. And it could be the dark matter, if it's primordial black holes, could be as heavy as 10 solar masses. So we really have no idea what the mass of a unit of dark matter is. But what particle physicists seek to observe is dark matter particles in this range and all the way to the Planck mass if they interact with ordinary matter. And so I like to show this cartoon to illustrate the search. The Earth is going around the sun is going around the galactic center, and we face a headwind of these dark matter particles that we seek to observe in our laboratories.
Thank you, Suman. That was actually a nice introduction of dark matter to the audience, and it's a really interesting and cool topic. But I also want to know from Joel, from an artist perspective. Joel, I know you are one of the artists at Drift Art and Dark Matter, and you are also asked to do an artistic residency, and you are basically invited to create some artist work for the dark matter as such. I just want to know, is this like the first time when you were introduced to the concept of dark matter, or how did you get the interest to the dark matter topic as such?
Hi, so it's really nice to be here with you both, Gurpreet and Simone, and with everyone out there in TV land. So I've been working in physics for about 7 or 8 years. So I've visited lots of what I call landscape laboratories, which are essentially neutrino detectors, which were once thought to be a candidate for dark matter. And, you know, I've been working in Siberia at Lake Baikal, where they turn the oldest freshwater lake into a telescope dedicated to the center of the galaxy. I've done research and scholarly articles on the IceCube Neutrino Observatory, which is embedded in the geographic South Pole in the ice shelf, 2 kilometers under the ice, sitting on the bedrock. And it's a cubic kilometer scale detector. And I've been in Gran Sasso, Laboratorio Nazionale del Gran Sasso with CUORE, the Cryogenic Underground Observatory for Rare Events, which is supposedly the coldest object in the observable universe, which, by way of temperature, exits our galaxy, if you want to call it that, our universe, because it dips below the thermal relic radiation background, cosmic microwave background. And I'm working with the SFB 1258 at the Technical University of Munich, who are developing a neutrino dark matter detector in the Pacific Ocean, collaborating with an oceanographic institute called Ocean Networks Canada. So I've been following physics for a long time. When I did my undergrad in Toronto, I did the history, philosophy of science, and I've been kind of into physics since I was about 18 years old. And I read Stephen Hawking's A Brief History of Time. And ever since then, I've kind of been on this incredible adventure with physics and landscape and arts and music and poetry and plurality. Do you want me to show some work? I don't know. Was that an? Do you want me to give you some more examples?
Yeah, sure. I think that would be awesome.
Okay, so you should be able to see this. So NLAND, the holographic principle, is made at SNOLAB, 2 kilometers underground in a class 2000 clean lab, where deep 3600 is, where I think you both are working on that project. And, you know, I got pretty interested in this essay that was shared with me about future particle colliders and how you might be able to detect dark matter through collapsing black holes inside of future 100, what is it, tera electron volt colliders or something like that, or is it giga electron volt? I can't remember. But in the collapse of these black holes, I don't remember the logic of it. Maybe you know, but you would also perhaps not only get a kind of printout of all the possible particles in the universe, including dark matter, but even ones we don't know about. You would also, you know, get proof of this like multiple dimensions that's used in, especially in string theory, or, you know, there's 11 dimensions in string theory, or there's infinite dimensions in some quantum field theories and stuff like that. So I got really interested in these multiple dimensions of physics because as an artist, you know, I think things like quite poetically, plural, multivocal. So to me, like dark matter is something that is imperceptible, that we know is there, but we don't know how to measure. And so I kind of read it. I'm trying to read the site of SNOLAB, for example, and considering other things that we we know is there, but maybe isn't so explicit, either in the telling of science or in our societies, you know, things that have gravity, but maybe we don't know how to respond to it so well. This is a little clip from Siberia, where they were cutting the ice to submerge like photomultiplier tubes into the water. This is a video installation that was in the University of Toronto a couple of years ago. And that was shot at Laboratory Nazionale Gran Sasso with Cuore, the coldest object in the universe, which is under a mountain. And like SNOLAB and like Baikal and like Ice Cube Neutrino Observatory, all of these planetary bodies are essential parts of the technology. So you don't have SNOLAB without like 2 kilometers of granite over top, and you don't have Ice Cube Neutrino Observatory without, you know, a massive ice shelf. You don't have Laboratory Nazionale del Gran Sasso without the Gran Sasso Mountain over top. So all of these things become kind of technical, and it complicates the distinction between nature and technology. And in those complications, there's a lot of like generative misunderstandings. To think about other kind of metaphysical issues, that's not just space, time, and energy, but those things as well, but nature and technology and the kind of troubled category of the human, and the kind of role that the history of science has had in developing these concepts. Yeah, this is cool. This is an installation of NLAND, but when it was shown at Agnes, and every time I install it, it's always different, which is really enjoyable. But here we're looking at this thing called plug plate. Okay, and a plug plate was used in the Sloan Digital Sky Survey, and essentially what it is like this aluminum plate, and it's a kind of lens blocking device, and you can see all these like little holes in it, or little circles, and in those little circles they drill a hole, and it allows a specific starlight to pass through. So there's a bunch of holes drilled into this thing, and they attach to this telescope, and or some big type of camera, and they allow these like starlight, just specific starlight, to pass through, and they make thousands of them, thousands of them, and they take pictures of the sky, and then they can make like this 3-dimensional model of the sky from Earth. So this is what's happening in NLAND a lot, is there's this projecting between dimensions, you know, like, so if you look at this thing, it's like flat, it's like one-dimensional in a way, but it's doing like a 3-dimensional technique, you know. So this, I'm really interested in this collapsing of dimensions from 7 dimensions to 3 dimensions, from 1 dimension to 5 dimensions. These type of plays with space really influenced a lot of the work that I was doing. And again, to kind of bring it back to dark matter, like the idea of the imperceptible or the translucent, when reading the site of SNOLAB, I was also looking at like the Robinson-Huron Treaty, which is the territory and the treaty that allows the kind of mining company to be there, that allows SNOLAB to be there. I was thinking about the meteor like 1.8 billion years ago that impacted the Earth and fractured the mantle and allowed all that copper and nickel to emerge in the first place. And kind of like, you know, trying to account for all the different elements that make this kind of prize-winning new knowledge of reality possible. This is a kind of situating practice.
Yeah, that's amazing. Thank you, Joel, for showing those nice arts about the dark matter. And Simon, I'm again curious, how you became interested in the dark matter, and how you get involved in the search of dark matter, and why you specifically connected to Deep 3600 project only for the search of dark matter. Can you say a few words about that?
Yeah, so personally, when I started in particle physics in 2008, I started at the Large Hadron Collider at CERN in Geneva, looking for new proton-proton collisions at tera-electron volts energies. And in doing that, we rediscovered the standard model of particle physics, but also what we were looking for is new forces of nature, new particles that have never been seen before. Some of these particles could be dark matter. And so after having spent 10 years researching with Atlas during my PhD and postdoc, I wanted to join the Deep 3600 experiment at SNOLAB to look for dark matter more directly using this underground experiment. And so that's what I did when becoming a faculty member at Carleton University.
That's amazing. And Joel, I have a question for you again. Can you tell us something about your experience at SNOLAB? Like, how did you get the idea to process the actual information about the dark matter, or the process, which is basically the N holograph, which you made as a part of art for the search of dark matter? So would you share a few words about that as well?
Yeah, of course. Yeah. Oh, geez. I had always wanted to go to SNOLAB. There was something kind of mystical for me about like entering 2 kilometers into the Earth, because I grew up like really rural. I grew up in a forest near a river, on contested indigenous territory. And yeah, I was just, you know, when I got that email inviting me there, I was kind of ecstatic about it. And one of the things that really struck me, I don't know how many people out there know, but when you go to SNOLAB, you're going through this Carleton mine, and you go down a shaft like that's 2 kilometers long. And depending on how many people are in the shaft and how many stops along the way you have to make, it can take a while. I think the first time I went down, it took me like 12 minutes to get down. But another time it only took 5 minutes, and it go really fast, and you get like the reverse ear popping, you know. And then you get down there, right? And you got all your mining equipment on, and you got this headlamp, and it's dusty, and there's this weird smell because they spray stuff to keep the dust down, and it's loud. It's really, really loud, right? Because they're pushing all this air all the time because it's hot. and because workers down there need oxygen. So there's all of these tunnels underground, like on different layers, and they're all kind of connected, and they're whistling and wazzling all over the place. And then there's all this air going through it, like boom. And I was like, wow, this is kind of this is like a big planetary scale organ or something. So just approaching SNOLAB, I was already like, whoa, with my recorders, like recording all these sounds and finding these kind of pockets of standing waves. There's really deep resonances and stuff like that. This is really like kind of quotidian look at the approach of like a dark matter laboratory. Okay, so it's like you pass through mine, so you get really dirty. Okay, and then you get to the lab and it's suddenly really clean and it looks cool and you're like really excited. And then you have to like take off all your clothes and have a shower because it's a class 2000 clean lab. It's like one of the cleanest labs 2 kilometers underground on the planet. It is the cleanest lab 2 kilometers on the ground, and it's the only one. So that's kind of like already really cool, right? But then you enter into this zone in this territory of how is it called, like low background. So the reason that, like I was talking about before, like all these things are under the mountain, or this one's like 2 kilometers inside of this meteor impact basin, is because they want to get rid of like all this surface radiation. So you go down there and it's low background, meaning there's not all these whistling, wazzling particles like passing through everything all the time, like this crazy noise that we live in up here. You go down there and it gets kind of like quiet, which is weird because I just told you it's really loud down there. But like radioactively, it's super quiet. And then that allows them to kind of look for these needle in the haystack. So when you go down there, you get rid of all this noise. If we could see it right now, we probably wouldn't even see each other because there's so much stuff like flying all around, you know. But down there, it's like whoosh, whoosh, like this, and that gives them the space to see these really rare, kind of low energy events. And they have all these amazing like liquid argons and tellurium dioxide crystals. And what does Deep 3600 use, for example?
Liquid argon.
Yeah, liquid argon.
I have a few slides about this if we want to talk about that.
Yeah, I mean, I'm totally interested in like the elemental bits that allow things to be measured or invited into our territories.
Yeah. And my next question is actually related to that SNOLAB thing. Simon, can you tell us why that SNOLAB is exactly where it is? I mean, like underground in a mine, and what's the actual importance of having that lab underground beneath 2 kilometers under the surface of that?
Yeah, absolutely. So first I'll describe what is Deep 3600, how we are sensitive to dark matter, and what our latest results are. And then I'll answer this question about SNOLAB and why quantitatively. But Joel already gave a great explanation. So I'll only show you a few more. So this is the Deep 3600 during its construction. At its heart, Deep is an acrylic vessel that is meant to contain the 3.3 tons of liquid argon. And on each of these sites here, a light guide, an acrylic light guide was bonded. And on each of the light guides, a photomultiplier tube, which is our very sensitive light detector, was installed. So here, the photomultiplier tube is looking inward into what will be filled with liquid argon. And this all rests into a steel shell. And there are other photomultiplier tubes, PMTs, looking outward into the water Cherenkov veto. That's in case any of the muons from the surface make it all the way through the 2 kilometers of rock and go into our detector. They will produce some light that we can detect here. And if these vetoes detect light, we know it's not dark matter. We think it's a muon from a cosmic ray. And so here's a cartoon of the inside of Deep 3600. There's this liquid argon And the way it works is if there's a dark matter particle coming in, it will collide with an argon nucleus. And this argon atom will be excited. It will form an excimer, an excited dimer with a neighbor, becoming argon-2 excited. And when this dimer de-excites, it produces a particle of light, a photon of UV light. Now, our detectors are not directly sensitive to UV light, which is why we need a wavelength shifter to convert that UV light into blue-violet light. And it's this blue-violet light that travels through the light guide to our PMTs for detection. So that's the operating principle of DEEP. Now, it's not that simple because, as Joel mentioned, there are many backgrounds that can mimic the signal from a dark matter particle. But fortunately, we have handles to remove those backgrounds and be sensitive to dark matter interactions. This is an artist's view of what happened when a dark matter particle goes in and the creation of this flash of light. And so if we look at all the events that we detect in this plot, 4.4 days of operating the DEEP detector, this is our first dark matter search that came out in 2018. The y-axis here, the vertical axis, is how prompt the light was emitted. And this here is a number of photoelectrons, so that is correlated with the number of photons detected in total in the detector. And so this axis here is proportional to the energy of the impact. And we can't even see the dark matter region of interest on this plot. It's this red box here at the left between 100 and 200 PE. And so it's all the way to the left here, while the other events either are separated in F prompt, in the prompt fraction. You see here these argon-39 beta decays, some gamma particles that are in the detector. These are all radioactive backgrounds in the detector, and also trace amounts of isotopes that decay through the alpha emission. They emit a helium nucleus. These are these full energy alpha decays, but sometimes when we don't detect all the light, or sometimes when the track length of the alpha and liquid argon is very short, we get potentially some leakage in the dark matter region of interest, which is why we need to other discriminants than these two variables to be able to say, oh, is this a potential dark matter candidate, or is this just an attenuated alpha, a neutron scattered? This is what makes the analysis difficult. That's what Gurpreet and I and the whole collaboration are working on figuring out. Zooming in to the low energy region here, this is our result with 1 year of data. We've published the data from November 2016 to October 2017. And in between those beta electrons, these alpha particles, we were able to construct a region of interest here that is free of backgrounds and where we are sensitive to dark matter particles. So if there were dark matter particles detected during that year of data, we would have seen many dots right here, maybe a few events in this year period, so a few events per year. These are very rare processes. Didn't find any, but we were sensitive, which allows us to exclude some of the parameter space. You'll see this plot repeated a few times, and the results I'm about to show. This vertical axis is how strongly dark matter interacts with nuclei in the argon. And this axis here is the unknown mass of dark matter particles that I've hinted at before. And so here, so 1 GeV here, again, that's about the mass of a hydrogen atom. So that's 1,000 of them. And this is the range we're looking at, 10,000. And this here, above the red curve, is a region excluded by deep data. In other words, if dark matter had these parameters, we would have seen it. And so the fact that we didn't see anything, we're able to conclude that it's not there. The dark matter could still be down here. And so that's why I like to compare particle physicists with explorers. There's this unexplored parameter space. We don't know what particles could be down there. We need more sensitive experiments to push the sensitivity and get observations, or if we don't see anything, be able to rule out new regions, to be able to explore new regions of the parameter space. Some of our latest results is that we've expanded this search to look for other velocity distributions. This is 16 examples of different velocity distributions for dark matter. If you remember this cartoon, there's uncertainty on the velocity that dark matter particles have with respect to the Earth. It can follow any of these distributions. And that's how our results in the same axes change for different assumptions on the velocity distribution. And we've also explored what happens if dark matter couples more to argon than to other nuclei, more to argon than xenon or than germanium or other target materials that are used. And in some of these, this parameter space, Deep 3600 is actually the leading experiment in sensitivity in the world. So we're leading sensitivity for a range of isospin violating dark matter hypotheses. And then I'll conclude with our very latest result, 2022, fresh off the press. Here, we're not looking for hydrogen atom-sized particles. We're looking for grains of sand mass particle. This is this Planck mass type particle. These particles would be much more sparse, but also the signal they would leave in our detector would be unmistakable. And so we have a different analysis, different event selection, looking for these particles, different backgrounds. In the end, when we looked in the region of interest, we found no event, no candidate event, which allows us to exclude this region in the same parameter space, interaction strength versus dark matter mass. But you'll notice here, we're not in the 10 to the 3, 10 to the 4, we're between 10 to the 8 and 10 to the 19 GeV. And Deep is really the first one to exclude this part of the parameter space here, dark matter particles with the mass of a grain of sand. And so that's what's exciting about our new result.
That's amazing. Thanks, Simon, for the great introduction of Deep 3600. And yeah, just also adding to the introduction of Deep, we are like the collaboration of about 100 physicists from 25 different institutions around like 8 countries in the world searching for this unknown dark matter particle. Also, my next question is for Joel. You already said your interest about the SNOLAB laboratory, but I just want to ask a few more things. Why that laboratory is particular interest to you, like the SNOLAB, and you call it as like a landscape laboratory as such. So what's the things that interest you about that laboratory, or why you specifically choose that for your artwork?
Yeah, thanks for that question and the run through of Deep 3600 and everything. I'd like to show you something. I'll get to your question, but I want to show you something that I think is kind of cool, which is we made with Snow Plus. Let me share my screen. Sorry. We made this kind of selfie with Snow Plus. I'll show it to you. As soon as I remember how to share a screen. Here we go. So if you can see my mouse, we were standing up here like these tiny little humans on this giant detector. And all this noise that you see is actually, our particles decaying and us stepping on this thing up there causing these particles decay. So when we're not up there, you don't see these particles. It's quiet, and you just get some once in a while. And if they happen to travel faster than the speed of light, it'll set off this Cherenkov radiation. That's essentially how a lot of these detectors are operating with these different elements. Is it will, something energetic will hit this particle and accelerate it faster than the speed of light in the medium, and when it does that, that radiation, and then they see that specific wavelength of radiation and they amplify it or what have you. And then they kind of do these analysis. And I remember when I was a kid, like growing up, like nothing travels faster than the speed of light, nothing. It's like Einstein, everybody knows that. You learn that like when you're 5 or something. Then later, if you scratch the surface, it's like, no, that's not true. Nothing travels faster than the speed of light in a vacuum. But we don't live in a vacuum. There's stuff traveling fast at the speed of light all around us all the time. And I find that like really fascinating, because it's another thing where you can kind of start to unlearn things, and you can start to like take a critical look at stuff. And physics offers a sort of pharmacological perspective of positives and negatives. And this critical element, I think, is really important. So if you'll forgive me, I'm going to exit this screen for a second so that I can actually respond to your question, which was about landscape laboratories. Okay, so SNOLAB to me is similar to all of these other laboratories that I already mentioned to you. For example, the IceCube Neutrino Observatory, the Laboratory Nacional de Gran Sasso, the gigaton volume detector in Lake Baikal, and geez, where else have we been? There's a bunch of them like in the States, they're just all over the place. And I have this really nice slide. Here it is. Okay, so I'm going to talk to you about a landscape laboratory for a second on a little different scale. Okay, so for me, like a landscape laboratory is a vast technological assemblage that's embedded in some sort of environmentally protected planetary body, such as the Antarctic ice sheet. So the LNGS in Italy is also in a UNESCO World Heritage Site, and IceCube, like the whole Antarctica, is part of the Antarctic Treaty, and Lake Baikal is also a UNESCO World Heritage Site. And so it kind of wrapping up physics with environment and ecologies and things like that. So the entanglement of elemental body with optical and institutional megastructure produces significant challenges to Western paradigms and traditional narratives and like our metaphysical ideas of nature and technology, which I mentioned before. And so I try to harness those to make non-standard critiques of these kind of disciplines and with troubled histories and things like that. So this is, like I mentioned, it's a cubic kilometer neutrino detector, 2.5 kilometers under the ice. And to the right is that paper I mentioned that's in the Anthropocene Review Journal. And we use that to kind of critique this notion of a technosphere. So I kind of am like this, if these things were an object that you could hold, and you just have one look at it, I kind of like try to flip it around so you get another look at it, or you can see through it, and then you get a kind of kaleidoscopic perspective on like different elements that make it possible. And I'm really interested in the landscape laboratory because it's where cosmologies cross. Once you start to think of cosmology in a kind of physical, astrophysical mode, that's very interesting, and physics is fascinating for like making you like think at the edge of what is possible, right? But then I like to think like of cultural cosmology and storytelling and mythologies and stuff like that as also relevant to the land where these places, where these kind of new order of observational techniques exist. And the fact that it's necessary that they're in the land, that they're in the element, is like a different way of thinking. It's like a whole new order of perspective. And so for me, they're like really rich philosophical sites. And I wrote a whole PhD about it. I just did a viva like in December, and it's called Quantum Ecologies and Cosmological Infrastructures. And it's a much more in-depth, obviously, like account of what landscape laboratories are, the history of physics, all that type of stuff. And it's like my Deep 3600 is this project called Radioamnion, which is in the Pacific Ocean, 300 kilometers from the shore of Vancouver Island and 2.5 kilometers underwater. And it's part of this Ocean Networks Canada Marine Monitoring Network, which is unprecedented. And this is a model of it here, and it's a sound sculpture that during the full moon will play a new artist's sound into and for the ocean. And so this module is actually part of a neutrino telescope that's being tested there in the ocean. So it's going to be this kind of vast thing. And the website for it is radioamnion.net. And since it happens every full moon, it crosses again these cosmologies. So it kind of is, it's kind of thinking with like ritual and mystical and talismanic notions, but it's also attached to oceanographic monitoring stations and physical cosmology things. And they're all kind of in this place, like kind of offering a new type of story, a different type of story, other ways of knowing, you know, and kind of pluralizing the kind of narrations that we need to be able to learn. Because if we think about like climate denialism or science denialism, for example, I think in Ottawa right now, you're kind of like living through like an extreme of science denialism. And part of that denialism is because the way that it's been told in the past and maybe still being told needs to be kind of like re-updated and rethought. And I think a lot of work needs to be done to like account for histories and land and elements in the co-production of knowledge and things like that.
Actually, that sounds interesting. That's actually amazing. So I also have one question to both of you, actually. What's the actual importance of collaboration, basically? For example, to tackle the problem of dark matter, I would say, because like since we know for the Deep 3600, it's an international collaboration of more than 100 physicists working on this project. And in your video and Ned as well, Joel, you mentioned, I actually heard a voice of one physicist who said that we need to basically expand our toolkit or to basically include the interdisciplinary or more multiple perspectives to tackle the problem. So what are your thoughts exactly about the collaboration or importance of collaboration for this project?
Joel, do you want to start?
Yeah, I wasn't sure that was a question for me. Yeah, I think, you know, Miriam Diamond is this, you know, award-winning physicist in Canada, and she kind of narrates that video and speaks like about what you said, expanding the toolkit. And I don't want to put words in her mouth. It's, you know, I left it a little bit open in that, but essentially what we're talking about, and I think it's completely different in Canada, but in Europe where I work, a lot of the people, it's a very, it's not a very diverse field, physics, or it hasn't been. In Canada, it's totally different. I think it's really progressive compared to sites in all the other sites I mentioned. So it's kind of, you know, that's kind of what collaborating across like these difficult terrains of whiteness, really.
Yeah, we do have to make an effort to make science, physics in particular, way more inclusive. And we are making progress in Canada, but there's much more to be done. I'm showing this diagram of this map of SNOLAB to show you, well, in part what Joel described, the snow detector, the deep detector is here, but also to highlight that physicists can never have done this by themselves. This is really a very multidisciplinary collaboration with engineers, technicians, geologists, chemists, biologists, and of course, a huge contribution from the mining industry in Sudbury to make this a reality. I'll skip this slide. I'm looking at the time, but this is explaining how we reduce the cosmic background rate from 14.4 million muons per meter square per day at the surface, going through us, going through everything, to only 0.27 muons per square meter per day by the depth of SNOLAB. And they're really building our experiments there. It was challenging from a technical point of view. It's absolutely necessary. And this is the picture I have of SNOLAB. Once you get past the shower, once you go in the clean room, so not only is SNOLAB very deep, it's also very clean. And these are two absolutely necessary conditions for our experiment to work. I want to show our collaboration pictures. This is also deep collaboration is 100 researchers from 9 countries. About half the collaboration is Canadian. This is from a pre-pandemic time when we all traveled to Mexico for a collaboration meeting. And then we had a collaboration meeting in Munich. I'm showing these different pictures. You see there are different faces. Our collaboration keeps evolving. 100 people, that's at one different time, but if we integrate over the years that we've been collaborating, it's many more. And now we've just had our first back in-person meeting in Sudbury, Warsaw, and online. And we're having another collaboration meeting soon. And I also want to thank funding agencies and partners for making all this research possible. It's really governments from many countries coming together internationally to make these experiments a reality. That's part of the collaborative aspect of science as well.
Yes, that's amazing. And it's actually a very good experience to work with the collaboration as I'm working with the 3600 right now. So yeah, the main or the big theme for this exhibition was basically to see the confluences between the artistic and the scientific work. So it's actually great talking with you, Joel and Simon. So would you like to add anything to the chat, or you want to say something, how you are specifically working from your own field for this dark matter research?
I'd be curious to take a few questions from the audience.
Yeah, I think that we're almost at time. Fiona, can you, I know that you've been monitoring the Q&A. Can you facilitate a couple of questions before we conclude?
Sure. I think we probably just had time for one. But I thought because we've had so much interest in this, so this question's from Mark Richardson, who actually, along with Zach Kenny, they're both at McDonald Institute, were super helpful in bringing this event together as well. And but Mark had this question about audience in both of your practices, and really who you do this research and work for, and who do you imagine it to be for, or maybe Joel, in the case of you, who do you imagine kind of experiencing your work, and Simon, who do you imagine that you're doing this work for? Maybe it's not a who, but a why, or a kind of bigger question. But who's the audience?
Wow, difficult question. So I think the audience is, of course, there's 120 people left here. So all of you come from all different walks of life. Some of you are into art, some of you are into physics, some of you probably ain't even into either of those things, and you arrived here somehow. Yeah, so I would, sometimes it's for humans. A lot of time it's for humans. But in the case of Radioamnion, we're trying to, make contact with the ocean, like in Stanislaw Lem's Solaris, for example. the sentient ocean planet. So you know, Eve Tuck, Oscar Coagli, Michael Marker, all these amazing indigenous philosophers of place always talk about how land is wise and knowing, and some of the work that I do is also not for humans. It's for different entities and different forces, and like what they call more than human parliaments. Sometimes it's for the elements itself, you know, sometimes it's for the water, sometimes it's for the air, sometimes it's for Gurpreet, sometimes it's for Fiona, sometimes it's for Andy Berg, you know. Yeah, that's my take on it. All ages, ancestral and future.
That's a great answer, Joel. And I'd say that's true for art, but that's also true for what we do as scientists. We want to connect with nature at a fundamental level to try to understand it. And ultimately, that knowledge gets shared, and we don't do this for ourselves, we do this for humanity and beyond.
Oh, so great. Thank you both. And thank you so much, Gurpreet. That was wonderful. I really loved that conversation. Moira, do you want to come on and wrap it up?
Yeah, the only comments that I would have to add to today's conversation is, wow, it's almost overwhelming, but it certainly does beg those next steps, and that's to get over to the gallery to visit Drift and Art and Science of Dark Matter. I can't wait to see the exhibition. And I thank you, Gurpreet and Simon and Joel, for your time and your, you know, affording us this fascinating glimpse into your respective worlds. And thank you, Fiona, and the gallery for partnering with the Faculty of Science on this most excellent Science Cafe. Yeah, and thank you everybody for attending. It was a great conversation.
Yeah, thank you. Thanks, everyone. Have a great rest
Yeah,
of the day.
thank you. It was really cool, really fun. Thanks, Simone. Thanks, Gurpreet. Thanks, everybody, Fiona, Moira, and Simon and Mark. I said Simon already.
Yeah. No, thank you, everyone.
Thank you, everybody.
Yeah, it could have gone on a lot longer, but thanks.
Yeah.
Okay. Bye.
Ciao.
Hi, everyone.